Welcome to Stochastic Processes Lesson 7. If you got through Lesson 6a on the generating function, congratulations. If you chose to skip that, there's no loss. This is just going to take on from where we left off in Lesson 6. Lessons 3 through 6 were about two specific Markov chains, the gambler's ruin and the random walk. We now leave particular examples behind and return to the general theory. Everything in this lesson applies to any Markov chain with a finite or countably infinite state space. The questions we are answering is how to classify the states of a chain, which states can reach others. Once the chain is in a state, is it certain to come back? Those two questions turn out to be closely linked, and the answers organize the entire state space into a structure that makes long-run behavior tractable. We finished lesson 6 with the observation that a symmetric walk returns with certainty 1 and 2 in 1 and 2 dimensions, but not in 3 and above. That distinction has a name, and by the end of this lesson, we'll be more precise about that. In a Markov chain, two states communicate if there's a sequence of transitions with positive probability between the two states, and that goes in either direction. This is a little bit more formal statement here. I communicates with J if and only if the probability of going from I to J in n steps is greater than 0 for some n greater than or equal to 1. So communication is an equivalence relation. It's reflexive. Every state communicates with itself. It's symmetric. That's just by the way this is defined here. It has to be in both directions. In other words, I communicates with J and J communicates with I. And then transitive. So if I communicates with J and J communicates with K, I communicates with K. And that follows just from the definitions here. So from basic set theory, if you have an equivalence relation, that partitions your set into disjoint classes. So we're going to have for any Markov chain several classes of states where the states communicate amongst themselves within the class, but they have no communication, no probability of going into the other classes. That's what we're stating here. And then what basically that reduces the problem to just studying those disjoint classes. What I have on this slide summarizes what I was saying on the previous slide. A Markov chain with a finite or countably infinite number of states can be uniquely decomposed into a collection of disjoint subchains, in other words, sub-Markov chains, whose union is the entire chain, such that all states within a subchain communicate with each other, but not with other states. So that's what I mentioned in the previous slide. This is theorem 19 in my book. I'll give you a reference to my book, but most of the information in the book is in these slides. So this is just some bullet points related to this statement. Each subchain is called a communication class. The decomposition is unique. A chain with only one class is called irreducible. Irreducible means every state can reach every other state. So why does irreducibly matter? Many of the strongest results in this subject hold for irreducible chains and fail without that assumption. So as I mentioned before, the idea is that even if you don't have an irreducible chain, you can break your Markov chain into irreducible subchains, and then you can apply these various theorems that I've alluded to the subchains. I have some examples on this slide, two of which we've seen before. The gambler's ruin has three classes, in other words, three sub-Markov chains. We have all the states in the middle from 1 to a minus 1, and you could oscillate between these. But then once you hit an absorbing state, you can't reach any other state. So 0 and a are two single entity absorbing classes. So we have three classes altogether. In the unbounded one-dimensional walk, you can drift either left to the right, and there's always a probability of coming back to the state you started from. And so that this is irreducible, the entire chain has just one class. Then I have another example here on the slide, and there's three classes. I mean, maybe we need to study this a little bit. Let's look at the first one, 1, 2, and 3. So we go from, excuse me, 0, 1, and 2, not 3. So 0, 1, and 2 is you go from 1 to 0, from 0 to 2, from 2 to 1. You can also go back from 2 to 0. So these three communicate with each other, but you notice there's nothing coming out of this. You can't get out of these three. This probability is pointing away from 3. So this is one subclass. And then 3, you notice if you start in 3, you're okay in the sense of being in state 3. But once you're there, you either go out to 2 with probability 1/4, or to 6 with probability 3/4. So in the next transition, you have to leave. So this is a reflecting state, reflecting in two different directions. And this is one of the classes. And then you have something similar on this side here, 4, 5, and 6. You can go from 4 to 6 to 5, and you can go from 5 to 4, and you can go back and forth between 4 and 6. So these are all reachable from each other, but you can't get out of this. You only have a state a transition going into these three. So you have three subclasses in this Markov chain. Let's talk about the return time. Beyond whether the chain returns, we also care how long it takes to return to a state. So starting in state I, the return time is the first step at which the chain is back to state I, and that's a random variable, not a fixed number. And we define it here as tau sub I comma I. It's the minimum n greater than or equal to 1, such that x sub n equals I, where I is the state we started from. If no such n exists, then t sub I comma I is said to be infinite. The return probability is defined as follows here. The probability that tau sub I comma I is less than infinity, given that you started in state I. Okay, so that's the return probability. And then that gives us a basis for defining recurrent and transient. If f sub I comma I equals 1, then the state I is said to be recurrent. And if f sub I comma I is less than 1, then state I is said to be transient. Sometimes the term persistent is used. And just one caution here, I have almost the same notation that I used in parts lessons 5 and 6, and for that matter 6a. I used the notation that I'm pointing to here, f2n, and that was the first return probability from 0 back to 0 in 2n steps. So that's different from what we've defined up here. The way to distinguish them is that you have this two states, typically the same state, but there's a comma between them. And then this notation refers to first return probabilities, which we're really not getting back to anyway. So you can just stick with this meaning for the remainder of this lesson and beyond. We can also count the number of visits to a state. By the Markov property, each visit to state I is a fresh start. There's no memory when you have a Markov property. So the chain returns again with the same probability, f sub I comma I each time. If f sub I comma I equals 1, the state is visited infinitely often, hence recurrent. If f sub I is less than 1, the state is visited only finitely many times. Then we have this variable here, n sub I. It's actually a random variable, be the total number of visits to state I, starting from I. We can write it as the sum of indicator functions, counting one for each step at which the chain is at I, and the sum starts at n equals 0, so the initial visit is included. So this little indicator function here means if this is true, you count it as 1, and if not, you count it as 0. I have an explanation down here for indicator functions. Okay, and then here at the bottom, we have the probability that the total number of visits to state I equals n is given by this expression here, f sub I to the n minus 1, and then 1 minus f sub I. So this is basically a geometric distribution. You return n minus 1 times, then never again. That's this probability that you don't come back. So that's in the case where your f sub I is less than 1. You can actually compute the probability of the number of returns. And of course, in the f sub I equals 1, there's an infinite number, so you wouldn't use this formula in that case. We have alternate definitions of transient and recurrent on this slide. They're both based on expectation, but we're going to compute the expected value of the number of visits two different ways. So here, we're just using the known formula for the geometric distribution, and that's just 1 over 1 minus f sub I. And the state I is recurrent if f sub I equals 1. This blows up, and the expected value is an infinite, so you return an infinite number of times. And then if f sub I is less than 1, this is a positive number, less than infinity, and the state is transient in that case. Now, the other way of computing the expected value is based on this definition of n sub I using the indicator function, but I just want to highlight the indicator function I of a, just take any a for the time being, equals 1 if a occurs and 0 if a does not occur. So the probability that I of a equals 1 is equal to the probability of a, and the probability of I of a equals 0 is the probability of not a. So when you compute the expected value of I of a, you get 1 times the probability of a plus 0 times the probability of not a, and that equals the probability of a. So there's one-to-one correspondence between the expected value of the indicator function of an event and the probability of that event, and we'll use that here. So we take the expected value of n sub I given x sub 0 equals I, so the same thing we did here. But then we plug this in, and we take the expected value of this given x sub 0 equals I. And from what I just said down here, this is the probability of x sub n equals I given x sub 0 equals I. And this is just the sum over the probabilities of going from I to I in n steps, from n going from 0 to infinity. So once we have the transition matrix and we compute it for each value of n, as we've done much earlier lessons, and we sum those up, all these probabilities, we can actually sum the diagonal n-step probabilities and see whether the series converges. If it converges, then it's transient. The state is transient, and if it doesn't converge, then you have an infinite number of this becomes infinite, and that implies the state is recurrent. So that gives us another way of computing the whether or not a state is recurrent or transient. So we can, just in summary, we can compute the expected value two different ways, and each way gives us a different way or perspective in seeing whether or not the state is recurrent or transient. I have an example on this slide and the next. On the left, we have the example. We have a chain, Markov chain, with three states. State 1 returns to itself at the end of a step with probability 1/2, and it goes to state 2 with probability 1/2. From state 2, you either go back to 1 with probability 1/2 or on to state 3 with probability 1/2. After this, there could be other states, but for the purpose of the example here, once you leave 2, there's no way of getting back to 2, let alone back to 1. So I copied our definition of tau sub I here. It's the minimum over n greater than 1 of x sub n equals I. So in other words, the minimum coming back to the starting state. So the way we compute this is the minimum runs inside one particular path. So you fix a path first, and I have some examples I'll get to in a second. Then this quantity here is a set of step numbers for that one path, and tau sub 1,1 is the smallest element. The minimum is taken within a path, never across paths. So I have three examples here. Well, here is 1 going back to 1, and then to 2, and then to 3. Then it could go on. I have ... because maybe there's other states here. But so this is the path, and then the minimum return back to 1 is in one step. So tau 1,1 would be 1 here. Then we have another path, 1 to 2, 2 back to 1, then 1 to 2, and then 2 on to 3. So we come back to 1 twice, but we're interested in the minimum. So it's 1 to 2, 2 to 1, so that's 2. Then we have another path, 1, 2, and then off to 3, so you never come back to 1, so there's nothing here. And we say that tau sub 1,1 is infinity. The other point I wanted to make is every path of all the possible paths start in one of three ways. Either 1, 1, like this, and then what happens after that doesn't matter because, at least in terms of the tau, it's going to be 1, right? Because you came back in 1. I mean, you could oscillate between 1 and 2, 1 and 2 after that, but once you come back to 1 on the first step, you get this here, and that's probability 1/2, right? And then there's the 1 to 1 pattern for the path. That's like this one here. And once you go through those first three, which is probability 1/4, right? It's 1/2 and then 1/2 times each other. And there you get 2. And then the third pattern is 1, 2, 3. That happens as probability 1/4. And in that case, you have an infinite value for your tau. So we can compute F11. That's the probability that tau 1,1 is less than infinity, given that x sub 0 equals 1. So it's either 1/2 when you fall into this pattern, I should put it down here, this pattern here, or 1/4 when you fall into the second pattern, and you add those two, and so it's 3/4, which is less than 1. You don't deal with the third pattern because we're looking for when tau is less than infinity. So since F11 is less than 1, state 1 is transient. Okay, I have a little note here where the slip happens. It's easy to mess up on this, where you take the minimum over. You take it over one path at a time. So minimizing across all paths gives 1, the quickest return anyone could manage. And that is an ordinary constant, not a random variable, which tau is. The definition minimizes within one path F11 then measures the probability of the paths that return. That's what we did here. Let's continue with our example. I want to show three different ways of establishing that state 1 is transient. Since we've computed F11 and it equals 3/4, and that's less than 1, we know that by definition this is transient. So we've done the work on that already. Then we can go by expected visits. First we compute the distribution of returning to state 1, given that you start in state 1, n times, counting the initial visit. So you visit once when you start, and then you come back n-1 times. So that's each return is probability 3/4, and you raise that to the n-1 power, and then you leave after that. You go from state 2 to 3 and never return. The expected value of this distribution, being a geometric distribution, is 1/1 minus this number here, 3/4. So you get 1/1/4 or 4. And since this is finite, that means the state is transient. Then we go to the third method. We compute the transition matrix and raise that to powers. So we take the states 1, 2, and 3 and show the transitions probabilities between those. Then we raise it to the second power and the third power and so on. And we read off the values for the row 1, column 1, in other words, P11. And we get these numbers here. Then we need to sum them. Fortunately, we have a way of doing this. This looks rather formidable, but these numbers up here are the Fibonacci sequence, 1, 1, 2, 3, 5, 8, and so on. Each one is the sum of the previous two numbers, and the denominators are just powers of 2. There's a formula for the generating function of the Fibonacci sequence, which is basically this sum of these, and it's 1/1 minus z squared, where in this case z is 1/2, and so we get 4, and this is what we put up here is 4. It's less than infinity. The series converges, and therefore state 1 is transient. If you're interested in the details of this generating function, I give you a link here. It's on a Wikipedia page. It's actually the Wikipedia page for Fibonacci sequence, but this sublink takes you towards down the middle of the page where they talk about generating functions. And they have a slightly different form because they started with, they define the Fibonacci series to start at 0. And so their form is slightly different. They have z/1 minus z squared, where we need to divide by z since we're starting with 1 rather than 0. And so this is the right formula here. Okay, so let's continue. Recurrence is a class property. We'll show that on the next slide. It depends on this theorem here. In fact, this theorem does most of the work. If a state I is recurrent and communicates with state J, then J is recurrent. If I is transient and communicates with J, then J is transient. We can prove it here. Since I and J communicate, there exist K and M, so you can get from I to J in K steps with positive probability, and you can get from J to I in M steps with positive probability. One way to get from J back to J in M plus N plus K steps is to go to I in M steps, then loop at I N times, and then return to J in K steps. This is only one family of roots, so it gives a lower bound. So that's what I'm showing here in symbols. This is saying going from J to I in M steps, you loop it at I N times, and then go from I to J in K steps. So that's just one way of going from J to J in M plus N plus K steps. So this probability is greater than this. Then if we sum over this here, this is giving the probability of going from j to j in m plus k plus 1 steps and m plus k plus 2 steps and so on. And if we plug this in for this, we have a greater than or equal to. And you notice it's only the middle term has an n in it, so we need to sum over this. These just come out. And since I is recurrent, this sum is infinite, which means there's an infinite number of ways of returning from J going back to J, which implies state J is also recurrent. Okay, so that proves the first part. The second part follows. The transient case follows immediately by contradiction. If J were recurrent, this same argument that we just went through runs backwards would force I to be recurrent, contradicting our assumption in the second case that J is transient, that I is transient, excuse me. So this follows, and now we can proceed to prove the more general result, that recurrence is a class property. So from theorem 20, the theorem on the previous slide, if I and J are in the same communication class, both are recurrent or both are transient. For an irreducible chain, either all states are recurrent or all are transient. So this is the whole value of breaking your Markov chain into irreducible states, because you just need to determine the classification of one of the states, and that'll tell you what all the other ones are. So I have a few points here related to that. So recurrence is a property of the class, not individual states. For an irreducible chain, it is property of the whole chain. We can then simply call the chain recurrent or transient. And we have one more theorem on this slide. An irreducible Markov chain with a finite state space is recurrent. If every state were transient, then the chain would eventually leave each one for good, and with finitely many states, it would have nowhere to go. So this may seem intuitive also, right? If it's irreducible and you can't get out of that chain, and you only have a finite number of places to go, you're going to hit all of them. If you run indefinitely, you're going to hit all the states an infinite number of times, and so the chain is recurrent. Some takeaways from this lesson. Communication partitions the states into unique classes. One class means irreducible. In other words, if your Markov chain has only one class, then it's irreducible by definition. The recurrent return is certain, probability 1. Transient, it may never return. So there's only a less than 1 probability of coming back to the state. Recurrent, and we had some additional equivalent definitions. Recurrent if and only if the series of P sub I n diverges, and we saw that in our example. Recurrence is a class property, we just saw that. Finite plus irreducible implies recurrent. That was the second theorem on the previous slide. The return time is a random variable, not a fixed number. So that was the wrinkle in our example where we made clear that we needed to treat tau as a random variable and not as a constant. Then coming up in part 8, positive and null recurrence. Return is certain, so there's a case where return is certain, but the expected time could be infinite, or it could be finite. So that's this positive and null recurrence distinction. We'll talk more about that. The periodicity and why a chain can be recurrent, it never settled down. stationary distributions, the long run behavior. So for the finite irreducible case, for example, if you run your Markov chain indefinitely, you're going to see there's a probability of being in different states a percentage of the time, and that's computable. And this is useful in queuing theory, where you may want to know what are the probabilities that your queue is in these different states. Where irreducibility and aperiodicity earn their keep, so we'll talk more about that in the next lesson. So if you like this, please remember to give it a thumbs up and stay tuned. The plan is to have lesson 8, 9, 10, 11, and 12. So 5 more lessons after this.